So hello, my name is Mikołaj Koziarkiewicz. As you've heard, I'm working at SoftwareMill, and today I'm going to talk about cats. So for starters, show of hands. So who of you uses the library cats like regularly? Okay, quite a lot of people. Who uses Scalar as well, or instead? Okay. Right. So for the benefit of the general populace here, so to speak, cats is one of the two libraries that provide functional base for pretty much every kind of functional programming in Scala. So everything that does functional programming, all the libraries that you've seen on the talks are based either on cats or on Scalars. They are pretty much similar to each other because they're based on the same concepts. But today I'm going to be talking about cats. And by the way, one final check. Are there any cats here? Doesn't look like it. That's good. Right. So cats is a library for functional programming, as I said, right? But this talk is not going to be focused about that, at least not overtly. I may sneak some functional programming in. But the major focus is to use cats as a utility library, because cats has a lot of features that are quite advantageous to know about and to write in. Even if you don't use, tagless final, free, cake, Zio, or anything that will be alive or undead next year. So this talk is pretty much intended for everyone. Of course, the flip side is that if you are very experienced with cats, then you probably might know some of this stuff, but hopefully you will also find some interesting tidbits. Moving on. So the first feature I'm going to talk about is extension method constructors. And this thing is, let me just full screen this. And this thing is a nice, very small, nice feature that's maybe somewhat unappreciated. But I think everyone should know about this. So first of all, you can see there's this magic import of cat simplicits, which you usually use if you want to do anything about cats, and I'm going to talk about it later. And those method constructors that I want to talk about are specifically for option and for either. So you see here that if you import this cat simplicit, there's the extension method of sum, and it automatically gives you an option of int. There's a method for none, which is just you can just create an empty option, and the same thing for either. So you can have as right or as left. So what's the point of this, right? Because you can always use sum, none, right, left. Well, there are two things that are needed that are useful here. So let's start with looking at the bottom here. So here you can see, by the way, sorry about the var, so mutable state. Here you create an option that just by using none. And the problem here is that none is its own type. So you get this opt thing here is of type none type, right? And if you try to assign anything to it, it will fail because you can only assign a none. And the same thing is, of course, for sum. If you would use sum of x here, then this var can never be none, because it will be defined as sum. And the first advantage of this extension method is that they always within to the type that they represent. So they always return an option or an either, never like a sum, none, left, right. And here you see the example that this just works. So you define a none using the extension, the method from cats. It gives you an option of string, not a none, and then you can assign sum to it with a string, and it compiles. The other thing that's useful is that for either's at least, you don't have to define as many types. So if you look at the bottom again, you will see that this definition requires for you to input both types, because that's how write is constructed. And for cats, you just input the type of the other side, so to speak. So here you have as write int, which means the int goes to the left. And we know that a is a string, so that automatically goes to the right. And again, here we get an either. Here we get a write. Of course, you can screw yourself over in both ways if you don't input any type. So here we have an either of nothing and string, and here we also have an either of nothing and string. But at least here we have an either. So that might help you. And in any case, one more thing that's not mentioned on the slide is that when you have another thing that this is useful is for stuff like fold that have multiple argument lists and infer the type from the first list to the second, for example, because then you will get the correct type signature. Yeah, so that's pretty much it for that. Consider using it. Discuss it with your teammates. I recommend it. So next thing is a quite small thing from cats, and actually it's from cats data, which contains the various data types that are in addition to all the type classes from category theory that are in cats dot something. So if let's say you have a list of options and you want to map over it, so you can do it like this. And yeah, sure it works. Or you can use nested, which understands that you have a list of options. Specifically, that you have a functor of functors, because functor is what gives map. And you just can call this, and you have one less operation. And I mean, of course, it's also a matter of taste, but for me, it expresses much more clearly that you're making nested operation, and you see it in like one short step, instead of like having to mentally make a stack of operations. And the result will be the same. So you have to only call value on the nested as well, but the result is the same. And what's also cool about this is that it not only operates on functors, but also on applicative error. So all the riser or different other operators. It operates on traverse, so you can traverse in sequence from the inside out, so to speak, and many other classes. So yeah, so I encourage you to take a look at the documentation for nested and see whether it can help you with other stuff. Yeah, so now we're going to the import hierarchy, as I've said. So this is one of the things that that nobody ever bothered us to read about, and like literally takes you 5 minutes for it to understand. But it's always, like in the back of the head, and not knowing some things about the input hierarchy might cause problems for you, which take more than those 5 minutes. So this is my gift to you for saving that time. So. In the simplest case, you have, like I said, so in the cats X, that are like the core or kernel classes, which are like monad, applicative, functor, foldable, bifoldable, traverse, etc., etc., etc. And in cats data, you have validated, option T, nested, etc. So those are the additional helper classes that were devised for cats to simplify some stuff. And by the way, I didn't mention that earlier, sorry. So nested basically is, if you use monad transformers, is like a generic monad transformer, right? Anyway, so yeah, these two are like, you usually import them explicitly, but you also have this. Oh, yeah, font's different. Yeah, so you have two trees here. So one is cat syntax, and one is cat instances. Cat syntax provides those nice extension methods to everything. So for example, cat's either as right, cat syntax either is right is the extension method that gives you as right for everything. There is a cat syntax option sum. There is for monoids, there's combine. So everything that you call actually is in cat syntax. But to call those stuff, you also need implicit classes that provide evidence that, for example, something is a monoid, something can have either called, something is a monad, and either is an applicative, etc., etc. And this is where cats instances comes in, and it basically provides those type classes. Those members of type classes for different types. So cats instances either has instances of applicative and applicative error for either. Cats instances future has instances for monad for future, and monad error I think as well, and so on and so forth. So you can try to import those specific package object, but my recommendation is until you get experience with this stuff, and everybody in your team gets experience with this stuff, just use cats implicits, underscore, and import cuts, whatever you need, like from the core package or the data package. Because if you don't, and if you're not careful, and if you try to optimize too much, something like this can happen. So let's say we've started import cut instances option because we want to be smart and optimized, and we know that this is an instance for option, for pure, which is like the monadic value, the monadic neutral value. And well, we then remember that we actually don't have the syntax for that, right? Because we won't be able to write pure just like that. So we need the syntax. So we just say, oh, okay, let's import cats implicits. And yes, we get this error, which is weird because obviously we have this thing imported. So why does it happen? So here again is the hierarchy. It's a bit hard to see in the screen, but I'll try to explain it. So generally, I've removed the cats qualifier. So this is cat syntax, for example, right? So generally, you have the trees for the syntax and for the instances. Non-bolded things are traits, and the bolded ones are singleton objects. So as you can see, you got everything that provides the syntax or the instances is first made a trait. There's a corresponding object that you can also import if you just want that thing. And both those syntax and instance trees eventually go towards all syntax and all instances, which also have objects if you want to import those. And finally, implicits, cats implicits extends both of those two. So, so what happens in our example here? So we had first of all we had instances option and cats implicits. So we get instances option and we go to option instances through here. But since we are also importing cats implicits, we go from implicits to all instances, and we also get to option instances. So basically what the compiler sees is that we have imported the same object twice through different hierarchies, and well, it just confuses it. It doesn't know what to do, and hence this unintuitive error. I've literally discovered this particular picture yesterday. So that's one way to look at the import hierarchy. It's from ImpurePix. It's like it's a bit of a webcomic about functional programming in Scala. So basically, you can also look at this like difficulty levels in the video game. But the takeaway from this is you really only need to get good if you want to optimize, if your implicits are taking too much, and if your team knows how those imports operate. Otherwise, it's okay to play on easy mode. Right. So the next thing is semigroup and monoid. I mean, most of you have probably heard about this, but there's also the thing that everyone is talking about monad and higher abstractions. And those two type classes, which are very useful for a lot of stuff, like minor stuff that you can do often, are not mentioned very often. So semigroup is basically something that has this combine operation or like this plus operation. So you get something of a type with something of a type, and you produce something that is combination. It has the same type. The only restriction is the operation is associative. So like with addition, you just put parentheses in different places for like 3 addition operators, and you get the same result. And in fact, of course, integers form a semigroup under addition. Like if you add 2 integers, you get an integer, and the operation is associative. So it doesn't matter where you put the parentheses in the operation; it will always be the same. And monoid is basically an upgrade of semigroup, which is also gives an empty element, which is really the neutral element for the operation of combine. So for integers under addition, that's 0. Because if you add 0 to anything, you get the same number back. But the thing is that semigroups and monoids are really pretty much everywhere. Because lists, sets, collections, in general, well, most of them, are also semigroups and monoids. So you can combine, you can import cuts implicits, of course, and then combine the 2 lists and get a list with 2 elements. Same with a set. And of course, you might wonder why you do this in particular. So one use case, for example, is that you want to have a class that's backed either with a set or a list. And the thing is, the plus operation, like this, the collection, the appending of collections, is different for lists and for sets. So you can do, if you're writing generic code for like the superclass, you cannot write plus because you either have to choose the one from the list hierarchy or one from the set hierarchy. But if you specify that you want something that has a monoid for it, you can just use it with combine. And of course, yeah, lists and sets are monoids, not only semigroups, because empty list and empty set is a thing. So the other example is for strings. So strings are also semigroups, because you can combine strings. It's string concatenation, and you get a new string that's a combination of the 2. And of course, you have an empty element. An empty element for a string is an empty string. And if you combine with it, you get the same string back. And where the fun begins is that you can also do this for options. So if you can combine an option with another option, and you also get a result. So none here is empty. Yeah, so this is pretty obvious. But what happens if we actually combine 2 sums? Well, then it expects for the inner element to also be a semigroup. So as you can see here with strings, it works. And it concatenates the string that's inside the options. Same thing as for lists. So you have here an option of list and an option of list, and you get an option of list with the combined elements. One final thing to say about semigroups and monoids is that your data type can also be semigroups and monoids. So, for example, let's say you have a vector here, like 2-dimensional vector, basically, and let's say you have a person. This is probably obvious to you that this is a semigroup and a monoid, because you can add 2 vectors and you can have a neutral element. What about this? Well, it's not really a semigroup or a monoid, because you cannot combine 2 people to form another person that has, at least in this representation, any meaningful thing, right? You cannot, I don't know, concatenate the personal IDs. You cannot add the ages. It will not be a person. And that's the clue of differentiating whether you can or cannot combine stuff. because the combine operation requires for those two things that are combined, well, that the type, result type is the same. So it's not like with fold that it can be anything, or fold map. And writing instances for semigroup summaries is quite simple. It's only that you have to do a lot of additions because you have 4 elements. That it's kind of looks complex at first in this example. But for semigroup, it's even easier because from Scalar 212, you can use the shortened syntax that converts traits or abstract classes with one abstract member from functions. So this is basically the definition of combine here. So as a function, we only need to say that we want a semigroup here, and the compiler will figure out, okay, yeah. So this is the definition for combine. For monoid, unfortunately, if you don't extend from some semigroup, you have to write it the old-fashioned way with like a trait definition, anonymous implementation of trait. And again, this is quite simple. So you just give the neutral vector, and you basically have the same definition as above. Okay, and as a final thing, so something that will probably be useful to pretty much everyone at some point, and I guess that maybe at least some of you have used it. So again, cats also provides enhanced syntax based on category theory for tuples. So for all tuples, you get semigroup, monoid, and order. And of course, you can use that. So for example, here you get a neutral element for a tuple of list and an option, and it just infers from the types what are the type classes that are present, what are the neutral elements here. And again, as I said, so combine, so it's a semigroup, so combine also works, and you get those attributes combined in a way that should be expected. However, of course, for 3 tuples, I mean, if you have a lot of 3 tuples and 4 tuples, you should use some other representation of case classes. So this is only useful when you're working with tupled functions, for example, that sort of thing. So marginally, you should know that it's there, but it's not like you should rewrite your code to use this instead of case classes. Definitely not. However, and the other thing is, you also have to watch that those instances are compatible with what's inside. So here we have a trait A, and we have a pair of this A and some list, and this won't compile because there's no information about whether A is there is no semigroup for A. Simply as that. And this is where defining your own semigroups and monoids can help, or generate type classes. However, for pairs, it's even better because pairs are used much more often. At least they should be used much more often in the actual code base than 3 tuples and so on. And the great thing is that even cats has additional operators for those. So it provides instances for functor and bifunctor. So that's map is from functor, bifunctor is left map, and bimap. So it has foldable, which except for fold also provides for all and exists. So you can also do binary operations. It also has bifoldable. It has traversable, bitraverse, and the other stuff. So as you can see, some of those methods have a direction, and I'm gonna just show you why that's the case. So let's say we have a very simple pair here, right? Of an int and a string, and we call the map here. And as you can see, the functor on the pair is defined in such a way that this is right biased. So like if either. So currently, if you do a map on either, it maps on the right element. And of course, as you can see, you get another tuple back without deconstructing the tuple, without making matcher. It just works. And of course, you can change it to the different type, as in here. And if you want to map the leftmost element, so the first element, use left map. So it's also from bifunctor. And if you want to map both of the elements, you do by map. Again, this pretty much simple, works, is convenient. Just remember to import cuts implicits, as always. But there's more. So let's say you have a tuple of options of some types. As I said, there's by traverse, so you can call by sequence on that, and you get an option of a tuple. Just remember that you have to call this by, since, as I said again, those operators are right bias for tuple. So if you could just call a sequence, as you can see, it unwrapped or traversed the rightmost element, but left this one unchanged. So just, I think you should pay attention to when you're writing this. All right. So basically, I would have a lot more stuff to talk about, but we only have half an hour. So this is what I've chosen for this talk. However, I'm going to leave you with some further reading. You should try to, if you have the chance, if you have some time, you should try to read the cuts documentation, especially the documentation about data types, like validated, nested, option T, either T, etc., etc. You should definitely, especially if you're new to functional programming in Scala, you should read this book, Scala with Cats. It's by Dave Gornell and Noel Verge. I always recommend this book because it's a good book to learn functional programming in Scala, not only using cats. And this book is also is available for free in the digital version under this link. Also, if you're more advanced, I've just checked that Eugenia Kota, so this is his site, has mostly completed his series on herding cats, which is like his series on scalas, but for cats. And it's like it approaches the subject with like more category theoretical stuff. So he also explains how category theory ties into this type of functional programming. And finally, the base for this presentation. I mean, you can either copy this link or just go to blog.softwaremill.com and find it. Is also here, which I also recommend for you to see because it contains some additional stuff that's not mentioned here, and also that stuff is also like somewhat more advanced. So even those of you who use cats for a longer time may find something interesting here. Yeah, and we're done. So thank you.